Okay, so I'm just going to quickly go through the solution to this problem that we did in class. So we're using Kirchhoff's law to try and solve this complicated circuit and find out what the current is flowing through this point of the circuit. So we're just going to make an assumption about which way the current flows. I'm going to put an arrow on it showing it flowing upwards, and then we're going to apply Kirchhoff's laws, but we're going to try and make life as easy as we can by picking a crafty route through this circuit. The idea is basically to minimise the number of unknowns that we've got. Now we know in this case we're told that all of the EMFs, so all of the batteries, well, first of all they're ideal, so we can ignore the internal resistance, and all of the EMFs are equal to 12 volts. All the resistors, all of these are equal to 4 ohms. Now the trick is to find a route through this circuit that minimises the number of resistors that we pass through, because each time we go through a resistor we have to calculate IR, and if we don't know the current at that point then we have to call it I1 or I2 or I3, and so each time we do it we get another unknown, and that means we would have, for example, if we have 6 unknowns, we'll have to get 6 equations and solve the simultaneous equations. If we find a route that only involves us going through one resistor or one equivalent resistance, then we only have the one unknown, which is our current here. The current is going to go through these resistors, there's nothing we can do about that, but if we can avoid all other resistors we make our lives a lot easier. So let's just have a look at this circuit and have a look at a route. Well, if we go up through the route, we'll start at this point here, we'll go in this direction, keep going in this direction, go up through this EMF, across, down, again down through this EMF, and then across, down, down. We'll go around the outside now. We're going up through all these, but we're avoiding resistors wherever possible, because calculating the rise in potential, the sum of the EMFs, is straightforward. It doesn't involve the current. Keeping down here, down, and then we do, in order to make a complete circuit, we do have to go through these resistances, but as we'll see that's not too complicated. So I've got a circuit here which mostly just involves going through EMFs. Now remember, what we're doing is applying Kirchhoff's loop law. We're saying that the sum of all the EMFs is equal to the sum of the potential drops, the sum of IR. So I'm just going to calculate this bit for our loop to start with. Sum of all the EMFs. Remember, they're all equal to 12 volts, so we just go around the loop where we encounter a cell, or we're going through it in the positive direction, so that's plus E. We're going down through another one in the positive direction. Along here, that's another plus E, yeah, plus E, round, plus E. We're going through this one from positive to negative, so that's in the negative direction, so that's minus E, plus E, minus E, minus E, plus E. That's all of the EMFs. We're back to where we started from. Now a lot of these are going to cancel out, so I'll just cancel out the pluses and the minuses. So our total sum of all the EMFs is equal to 1, 2, 3, 4. And as I said, all the cells are 12 volts, so this is just equal to 48 volts. The next thing we need to do is work this side of the equation, so we go around the same circuit, calculating the drop in potential every time we go through a resistor. Well, so some of the IR. Well, we know that we've avoided all resistances when we go around the loop until we get to this point. We do then have to go through this combination of resistors. But remember, these are all 4 ohms. And we've got a relatively simple arrangement here. So if we're to represent this by one single resistor, well, we've got 2 4 ohms in parallel. So that's going to give us a 2 ohm. So we've got 2 ohm in series with a 4 and a 4 ohm. So the whole of this lot could be represented by a 10 ohm resistance. So in completing this loop, the potential drop is just going to be given by I times the total resistance for this section, which is 10 ohms. Now the way we've drawn it, we've assumed the current's going up here, so we're going through the loop, through these resistors in the direction of the current, so it is a plus I. So our total potential drop is equal to 10I. And now we equate these two things. Remember, sum of the EMFs is equal to the sum of the potential drops. So 48 is equal to 10I. In other words, our current I equals 48 over 10, or 4.8 amps. So there we go, we've made our life easy, not had to solve any simultaneous equations because we found a route that basically only gave us one unknown, which was the current we're trying to find.